What if everything we know about our future in space is just the beginning? For centuries, humanity has looked up at the stars with a mix of wonder and longing, dreaming of what lies beyond our atmosphere, imagining civilizations among the cosmos, and asking the ultimate question, are we alone? But here's the thing, our fascination isn't just about exploration. It's about transformation. Every leap into space, every discovery, every flicker of light from a distant galaxy isn't just science, it's a ripple in the fabric of human destiny. And right now, standing at the edge of a new cosmic era, we're on the verge of events so profound they could redefine everything from our daily lives to our place in the universe. Picture this, a single breakthrough in space technology could alter global economies, shift political power, or even answer whether life exists beyond Earth. A mission to Mars might not just be about planting a flag, it could spark the first interplanetary society. An asteroid deflection could mean the difference between extinction and survival. These aren't plot twists from a sci-fi novel, they're real possibilities on the horizon. And that's exactly what we're diving into today, 30 pivotal space events that could quite literally change the course of human history. Some are just decades away, while others loom farther in the future, but each one holds the potential to rewrite our story in ways we can barely comprehend. From the mind-bending discovery of extraterrestrial life to the construction of megastructures harnessing the power of stars, the next era of space exploration isn't just about rockets and equations, it's about moments that will echo across generations. Think of it like a domino effect in the cosmos. One event triggers another, and suddenly, the future we imagined is unrecognizable. So whether you're a space enthusiast, a casual stargazer, or someone who just loves pondering the what-ifs, this journey is for you. Buckle up, we're about to explore the breakthroughs, the risks, and the awe-inspiring turning points that could shape humanity's path among the stars. The countdown starts now. For years, the idea of worlds beyond our solar system felt like science fiction until the Kepler Space Telescope started uncovering them by the thousands. Imagine a planet not too close to its star to boil away all water, not too far to freeze solid, but just right. These are the worlds astronomers call Goldilocks planets, orbiting in the habitable zone where liquid water and maybe even life could exist. The discovery of exoplanets like Kepler 452b, a near-Earth twin, didn't just expand our cosmic map. It reshaped our entire understanding of how common life-friendly worlds might be. The hunt for these distant Earths relies on ingenious tricks. Telescopes like Kepler and TESS don't snap photos of planets directly. Instead, they watch for the faint dimming of stars as planets pass in front, like a moth flitting past a porch light. Others measure the subtle wobble of stars tugged by orbiting worlds. Each flicker or wobble is a clue revealing planets we'll never see with the naked eye. But here's what makes these discoveries explosive. If the universe is teeming with habitable real estate, the implications stretch far beyond astronomy. Suddenly, the dream of stepping onto an alien world isn't just a fantasy. It's a potential next chapter. Consider the ripple effects. Finding a truly Earth-like planet could ignite a new space race, not just to visit but to claim territory. Nations or corporations might vie to send probes, then crews, turning interstellar homesteading into a geopolitical reality. And what if we find more than water? Microbial life, or even ruins of a long-gone civilization, would force humanity to confront profound questions about our uniqueness in the cosmos. Even a single microbe on another world would prove we're not alone, rewriting biology, philosophy, and religion overnight. The search is already accelerating. Next-generation telescopes like the James Webb Space Telescope will analyze the atmospheres of exoplanets for gases like oxygen or methane, hints of biology at work. Projects like Breakthrough Starshot aim to send tiny probes to nearby systems within decades. With every new discovery, the line between science fiction and science fact blurs just a little more. We're not just mapping planets anymore, we're scouting the neighborhoods where humanity might one day plant new roots or meet our cosmic neighbors. A human footprint on Mars isn't a matter of if anymore, it's a matter of when. While the moon landing was a giant leap for mankind, setting foot on the red planet would be a quantum leap for our species. NASA Artemis program, initially focused on returning astronauts to the lunar surface, is essentially a dress rehearsal for Mars. The moon's harsh environment offers the perfect testing ground for the technologies and resilience needed to survive a world 54.6 million kilometers away at its closest approach. But the real game changer, partnerships with private companies like SpaceX, which isn't just planning a visit. Elon Musk's vision involves a self-sustaining city on Mars within our lifetime. The challenges, though, are staggering. Forget the 7-month journey through deep space, where radiation levels could exceed an astronaut's lifetime limit in a single trip. Or the thin, carbon dioxide-rich atmosphere that offers no protection from solar storms. The real test might be psychological. Imagine living for years in a cramped habitat with the same handful of people, knowing Earth is just a pale blue dot in the sky, unreachable in an emergency. Early Mars settlers won't just be explorers, they'll be pioneers in the truest sense, cut off from humanity in ways no one has experienced before. Yet the payoff could redefine civilization. A successful Mars colony would become a backup for humanity, an insurance policy against planetary disasters. It would drive breakthroughs in closed-loop life support, 3D printed habitats, and even terraforming technologies that might one day turn Mars's rusty deserts into breathable landscapes. And politically, the nation or entity that establishes the first sustainable presence on Mars could set the rules for interplanetary governance, sparking debates over property rights, resource extraction, and whether Mars should remain a scientific preserve or become a new frontier for capitalism. The race is already heating up. While NASA eyes the 2030s for a crewed mission, SpaceX's Starship, designed for mass transport to Mars, could accelerate the timeline. China, too, has Mars in its long-term sights. Every test flight, every prototype, every simulation brings us closer to the day when Mars colonist becomes a job title. This isn't just about planting a flag. It's about planting the seeds of a multi-planet society and forever changing what it means to be human. The discovery of even the simplest extraterrestrial life would send shockwaves through science, philosophy, and culture unlike anything in human history. Take Europa, Jupiter's icy moon, where beneath a frozen crust lies a global ocean with twice the volume of Earth's seas. Tidal forces from Jupiter's gravity keep that water liquid and possibly teeming with hydrothermal vents like those on our ocean floors, where life thrives without sunlight. When NASA Europa Clipper arrives in the 2030s, its instruments won't just study the ice shell. They'll hunt for organic molecules or plumes spraying potential microbial hitchhikers into space. Finding them would confirm life isn't a fluke exclusive to Earth, it's a cosmic inevitability. But Europa isn't the only candidate. Saturn's moon, Enceladus, shoots geysers of water vapor and organic compounds into space from its own subsurface ocean. Imagine a probe flying through those plumes and detecting amino acids or cell-like structures. Suddenly, the question shifts from "are we alone?" to "how many neighbors do we have?" And that's before considering Mars, where ancient riverbeds and underground brine lakes could still harbor extremophile organisms. Even if it's just fossilized bacteria, the message is clear: life finds a way. Then there's the ultimate paradigm shift: SETI detecting an artificial signal. Picture radio telescopes picking up a repeating pattern from a star system 50 light-years away. Mathematicians confirm it's not a pulsar or interference, but a beacon. Overnight, humanity would face an existential crossroads. Are they calling us? warning us, or is it just an ancient alarm clock left running by a civilization long gone? The psychological impact would dwarf the discovery of microbes. Religions might reinterpret scripture, governments would scramble to draft interstellar diplomacy, and every telescope on Earth would turn toward that patch of sky. But here's the twist: even a silent universe carries meaning. If decades of searching yield nothing, we're forced to confront the eerie possibility that advanced life is vanishingly rare, or worse, that civilizations tend to wipe themselves out before making contact. Either way, the search reshapes our self-awareness. Finding life humbles us. Not finding it makes Earth's biosphere feel like a miracle. The stakes couldn't be higher. We're not just hunting for aliens, we're searching for our own cosmic significance, and the answer might come from a single microbe in an alien ocean or a signal flickering across the void. Breaking the cosmic speed limit isn't just a dream. It might be a future engineering problem waiting to be solved. For decades, the idea of faster-than-light travel seemed locked in the realm of science fiction, bound by Einstein's unshakable rule: nothing can exceed the speed of light. But what if we could bend the rules without breaking them? Enter the Alcubierre drive, a theoretical concept that doesn't move a ship through space but instead warps space itself. Picture a surfer riding a wave. The water stays put, but the wave carries the surfer forward. An Alcubierre drive would compress space in front of a spacecraft and expand it behind, creating a warp bubble that propels the vessel at apparent speeds beyond light's limit, all while the ship sits still inside its own pocket of normal spacetime. The math behind this idea isn't science fiction. Mexican physicist Miguel Alcubierre proposed it in 1994 as a valid solution to Einstein's equations of general relativity. The catch: it requires exotic matter with negative energy, a substance that defies everyday physics. For years, that seemed like a deal-breaker, but recent experiments have nudged the impossible toward the improbable. NASA Eagleworks lab once tested a miniature warp interferometer, and while results were inconclusive, they sparked a crucial question: what if negative energy isn't purely fictional? Quantum mechanics already allows for fleeting particles with negative energy, like the Casimir effect, where empty space itself can exhibit bizarre properties. The gap between theory and reality might be narrower than we think. Now, imagine the implications. A functioning warp drive wouldn't just shave years off a trip to Mars, it would make interstellar travel feasible. Proxima Centauri, our nearest stellar neighbor, sits 4.2 light-years away. With current propulsion, that's a 70,000-year journey. But at even a modest warp factor, months, suddenly, colonizing exoplanets or mining asteroid belts in other star systems becomes practical. Trade routes could span light years, and humanity's footprint would extend far beyond the solar system. Yet the hurdles are as vast as the potential. Beyond the physics of exotic matter, there's the energy problem. Early estimates suggested a warp bubble might need the mass energy of Jupiter just to form. More recent calculations hint at ways to reduce that demand, but the engineering challenges remain staggering. And then there's the ethical dilemma. What if creating a warp bubble unleashes unforeseen consequences, like black hole formation or spacetime ripples that endanger entire planets? The race to crack FTL isn't just about bragging rights. Governments, private firms, and rogue researchers are all probing the edges of known physics. China's military has reportedly investigated warp drives, and startups like Applied Physics have published peer-reviewed refinements to Alcubierre's math. Meanwhile, physicists debate whether warp bubbles would violate causality, potentially allowing time travel, a headache for the laws of physics but a goldmine for storytellers. Whether warp drives remain a tantalizing what if or become the next great leap, one thing's certain: the pursuit itself is reshaping our vision of the future. Every failed experiment narrows the path to success, and every theoretical tweak brings us closer to a universe where the stars aren't just destinations, they're neighbors. The day we crack FTL won't just change space exploration. It'll redefine what it means to be an interstellar species. What if reaching space was as simple as pressing an elevator button? The concept of a space elevator, a towering structure tethering Earth to orbit, sounds like pure fantasy, but the science behind it is shockingly plausible. Picture a cable stretching 36,000 kilometers into the sky, anchored to a floating platform near the equator, with climbers shuttling cargo and crew into orbit at a fraction of today's rocket costs. No explosive launches, no disposable boosters, just a steady ascent into the cosmos. The key, carbon nanotubes, threads of carbon atoms arranged in a lattice stronger than diamond. These microscopic marvels could finally provide the tensile strength needed to withstand the brutal forces acting on a cable of that scale. While bulk production remains a hurdle, labs have already created strands centimeters long, proving the material's potential. The economic ripple effects would be staggering. Current rocket launches cost thousands of dollars per kilogram, but a space elevator could slash that to mere hundreds or even tens of dollars. Industries from satellite manufacturing to asteroid mining would explode overnight. Imagine entire factories in orbit constructing solar power stations or spacecraft in zero gravity, with raw materials ferried up the elevator. Tourism would shift from billionaire joyrides to accessible orbital hotels, and Earth's pollution from rocket fuels would plummet. The elevator wouldn't just lower the barrier to space, it would dismantle it entirely, sparking a second industrial revolution, this one off-planet. But the race to build it is as much about power as progress. Whoever controls the first space elevator holds the keys to Earth's orbital infrastructure, a strategic advantage akin to commanding the world's shipping lanes. China's already testing miniature climber prototypes, while Japan's Obayashi Corporation aims to have a functional elevator by 2050. Private firms, backed by tech billionaires, are quietly filing patents for stabilization systems and power beaming tech to keep climbers moving. The geopolitical tension is palpable. Will the elevator be a UN-administered public good, or will it become a corporate toll road to the stars? And then there's the existential risk. A snapping cable, whether from sabotage, space debris, or material failure, could whip around the planet at hypersonic speeds, unleashing devastation. Engineers toy with fail-safes like segmented cables or emergency detachment mechanisms, but the stakes ensure every design undergoes brutal scrutiny. Yet for all the challenges, the payoff is irresistible. A functioning space elevator wouldn't just change how we reach orbit, it would redefine humanity's relationship with the cosmos, turning space from a frontier into a neighborhood. The countdown to this towering achievement has already begun. Asteroid mining sounds like something ripped from the pages of a sci-fi novel, until you realize the math makes too much sense to ignore. Picture a single metallic asteroid like 16 Psyche, drifting between Mars and Jupiter. This cosmic nugget isn't just rock, it's a floating treasure trove of iron, nickel, and precious metals like platinum and gold, with an estimated value eclipsing the entire global economy. Now imagine spacecraft nudging such asteroids into stable orbits, where robotic miners extract their riches and shuttle them back to Earth, or better yet, to orbital factories. That's the vision driving companies like Planetary Resources, backed by billionaires who see space as the next gold rush. Their strategy starts small, with prospecting satellites scanning near-Earth asteroids for high-value targets, then scale up to extraction. The tech hurdles are real, but the payoff could rewrite the rules of resource scarcity. The economics are mind-bending. Earth's mines are finite, and digging deeper means higher costs and environmental damage. Asteroids, though, they're leftovers from the solar system's birth, packed with metals that sank to Earth's core billions of years ago. A single platinum-rich space rock could flood markets, crashing prices on Earth, but that's missing the bigger picture. The real game changer isn't bringing metals home, it's using them in space. Imagine constructing massive solar satellites with asteroid-mined aluminum, or 3D printing Mars habitats using iron harvested from space rocks. Suddenly, the cost of building in orbit plummets, and the space economy detaches from Earth's gravity literally, yet the roadblocks are as towering as the potential. Asteroid miners face a version of the cold start problem. You need infrastructure in space to mine asteroids, but you need asteroid resources to afford that infrastructure. Early efforts focus on ice-rich asteroids' water can be split into hydrogen and oxygen for rocket fuel, creating orbital gas stations to break the cycle. Legal murkiness adds another layer. The Outer Space Treaty bans national claims on celestial bodies but says nothing about private extraction, the U.S. and Luxembourg have already passed laws letting companies own what they mine, sparking debates. Will asteroid mining become a free-for-all, or will a regulatory framework ensure fair access? And then there's the wild card. What happens when trillion-dollar corporations operate beyond Earth's laws? A space-based Exxon or De Beers could wield unprecedented power, controlling the flow of materials that entire industries depend on. Nations might rush to secure their own asteroid claims, risking conflicts fought with drones and lawyers instead of bullets. Or perhaps mining consortia will emerge, pooling resources to share the spoils and the risks. The frenzy is already underway. While planetary resources faced setbacks, competitors like Astroforge are testing metal extraction in zero-G. NASA's Psyche mission, launching to its namesake asteroid in 2023, will study the object up close, gathering data that could prove invaluable to miners. Every probe sent, every lab experiment refining techniques, brings us closer to the day when a robotic claw grips an asteroid and pulls the first bucket of cosmic ore. The age of asteroid mining won't just add to Earth's wealth, it'll force us to decide who gets to profit from the stars and whether the next chapter of human industry unfolds in the void. The Moon has always been Earth's silent companion, but soon it could become our first off-world home. Nations aren't just racing back to the lunar surface, they're planning to stay. NASA Artemis program is more than a sequel to Apollo. It's the blueprint for a sustained presence, with the lunar gateway serving as a cosmic pit stop. This small orbital station won't just host astronauts, it'll be a springboard for missions to the Moon's surface and beyond, offering a place to refuel, conduct research, and test the technologies needed for Mars. But NASA isn't alone in this vision. China's ambitious lunar program aims to build a joint research base with Russia, targeting the Moon's resource-rich South Pole, where permanently shadowed craters hide vast reserves of water ice. Water isn't just for drinking. Split into hydrogen and oxygen, it becomes rocket fuel, turning the Moon into a galactic gas station. A permanent moon base changes everything. Picture a habitat with pressurized domes, powered by nuclear reactors or solar arrays, where scientists study low-gravity agriculture and the long-term effects of space living. The Moon's thin atmosphere and lack of magnetic field make it a brutal environment, but also a perfect lab for shielding experiments. How do you protect astronauts from solar radiation without Earth's natural defenses? Solutions tested here could save lives on future Mars missions. Then there's the economic angle. Helium-3, a rare isotope trapped in lunar soil, could fuel next-generation fusion reactors back on Earth. Mining it would be like striking oil in space, except this resource could power clean energy for centuries, but the Moon's real value might be as a launch pad. Escaping Earth's gravity burns a staggering amount of fuel, but the Moon's weaker pull means ships could depart for Mars or the asteroid belt with far less effort. Imagine lunar factories constructing massive spacecraft in low gravity, then launching them from moon-based railguns or electromagnetic catapults. The cost of deep space missions would plummet, opening the floodgates for exploration. The geopolitical stakes are just as high. Unlike Antarctica, the Moon has no international treaty governing territorial claims. Will bases become sovereign outposts, or will nations share resources under a new space-age UN? Tensions are already simmering when China lands its taconauts near a water ice deposit. Will they declare it a research zone or a de facto territory? The line between cooperation and competition is razor-thin. Private companies are muscling in two. SpaceX's Starship could ferry supplies to lunar bases, while startups like iSpace dream of robotic mining operations. The Moon isn't just a scientific outpost, it's the ultimate startup hub, where the rules are unwritten and the opportunities are as vast as the craters dotting its surface. Every rocket launched, every module deployed, brings us closer to the day when Earth isn't humanity's only home. The Moon base isn't just a stepping stone. It's the foundation of a future where the word Earthling feels too small for what we've become. A rogue planet drifting into our solar system would be the ultimate cosmic curveball, a world without a star, barreling through the darkness until gravity pulls it into our neighborhood. Unlike orderly planets tracing predictable orbits, this interstellar wanderer would be a free agent, its path chaotic and its influence disruptive. Picture Jupiter's massive cousin, invisible in the blackness until its gravity starts yanking on asteroids, tweaking planetary orbits, and possibly hurling comets from the Oort cloud toward the inner solar system. The ripple effects could range from celestial realignment to catastrophe. A gentle nudge might just shift orbital mechanics subtly over centuries, while a closer pass could trigger collisions that reshape the fate of Earth itself. Scientists have long speculated about these nomads. Some estimates suggest there could be billions of rogue planets ejected from their birth systems, adrift between the stars. Most would pass unnoticed, but one entering our solar system would offer an unprecedented scientific windfall. For the first time, we could study an alien world up close, one born around another star, carrying secrets of distant cosmic chemistry. Probes could sample its atmosphere, map its surface, or even search for signs of extreme life huddled around geothermal vents beneath an icy crust. The data might rewrite textbooks on planetary formation, proving some worlds are forged in the chaos of stellar nurseries and later cast adrift. But the risks would demand urgent attention. Even a small rogue planet could destabilize the delicate gravitational balance holding our system together. Neptune's orbit might wobble, altering the trajectories of icy bodies in the Kuiper belt. Earth could face increased asteroid impacts, or worse, a direct perturbation might push our planet into a slightly different orbit, triggering climate shifts that dwarf current global warming scenarios. Astronomers would scramble to calculate the intruder's path, while governments weighed the need for deflection missions or underground bunkers. The very uncertainty would fuel both panic and fascination, as humanity confronted a force of nature beyond our control. Yet amid the danger lies opportunity. A rogue planet's flyby could slingshot probes to interstellar speeds, offering a free ride into the galaxy. Mining corporations might eye its frozen volatiles or rare metals, turning a threat into a resource. And philosophers would face a humbling question. If a single rogue world can upend our fragile order, how many other cosmic surprises lurk in the dark? Whether it's a near miss or a close encounter of the destructive kind, this interstellar visitor would remind us that the universe doesn't play by our rules, and the next chapter of human history might be written by a planet that belongs to no one. Turning Mars from a frozen desert into a second Earth isn't just a dream, it's a puzzle scientists are already piecing together, one radical technology at a time. Picture atmospheric factories dotted across the Martian surface, sucking in thin carbon dioxide and churning out breathable oxygen. These machines, inspired by MIT's MOXIE experiment aboard the Perseverance rover, would work like artificial trees on steroids, gradually thickening the atmosphere to trap heat and melt ice caps. But oxygen alone isn't enough. Enter genetically engineered algae designed to thrive in Mars's harsh UV rays and low temperatures. Tanks of these tiny green pioneers could carpet the planet, converting CO2 into oxygen while releasing heat, jump-starting a greenhouse effect that might raise temperatures above freezing within centuries. It's not instant gratification, but it's a start, the real game changer, redirecting comets. By nudging ice-rich bodies from the outer solar system into collisions with Mars, we could deliver water en masse, creating lakes and even shallow seas. Nuclear-powered drills might tap underground aquifers, while orbital mirrors the size of cities could focus sunlight onto polar caps, accelerating their melt. Each step would feed the next. More water means more humidity, which traps heat, which melts more ice, a feedback loop nudging Mars toward habitability. Early settlers might live in domed cities, but their grandchildren could walk outside with just an oxygen mask, watching genetically modified lichens slowly paint the rust-colored plains green. Yet for all the ingenuity, terraforming Mars forces us to confront ethical landmines. Would seeding another planet with Earth life erase the chance to discover native Martian microbes hiding underground? Some argue Mars's ecosystem, if it exists, deserves protection, not pollution. Others counter that humanity's survival justifies reshaping dead worlds, just as cyanobacteria transformed Earth's atmosphere billions of years ago. The debate echoes colonial history. Do we terraform responsibly or repeat the mistakes of unchecked expansion? International treaties might require environmental impact studies before releasing algae, while preservationists lobby to designate Mars a cosmic wilderness. The stakes ripple beyond science. A terraformed Mars could become a geopolitical battleground, with nations claiming territory based on who contributed most to its transformation. Water rights, carbon quotas, and even sunlight distribution could spark conflicts. Corporations might patent engineered organisms, turning the red planet into a profit-driven experiment. And what happens if the process succeeds too well? An overactive greenhouse effect could render Mars uninhabitable for centuries, leaving future generations to fix our mistakes. Despite the risks, the vision endures. Every robotic mission, every lab breakthrough brings us closer to answering the ultimate question. Can we remake a world in Earth's image, or will Mars always remain just out of reach? The journey to terraforming isn't just about technology, it's about deciding what kind of interstellar civilization we want to become. One that treads lightly or one that reshapes planets to fit our needs. The choice, like the process itself, will unfold over generations, but the first steps are being taken today in labs and lecture halls where the blueprint for a second home among the stars is slowly coming to life. Imagine a fleet of robotic explorers fanning out across the galaxy, each one capable of building perfect copies of itself from raw materials found in space. This isn't just an idea, it's a theoretical reality called von Neumann probes, named after the mathematician who first envisioned self-replicating machines. Picture a single probe landing on an asteroid, mining metals and minerals, then constructing an identical twin. Those two become four become eight, and within centuries, a wave of exploration could sweep through the Milky Way without humans lifting another finger. The implications are staggering. Instead of waiting millennia for slow, fuel-limited missions, we'd unleash a self-sustaining army of cosmic scouts, mapping every star system and potentially unlocking the universe's greatest mysteries while we're still tethered to Earth. But here's where it gets eerie. The same tech that could revolutionize exploration might also pose an existential threat. A single programming error or mutation in replication could turn these probes from explorers into predators. Imagine a glitch that prioritizes replication over all else, probes consuming moons, planets, even stars to fuel endless copies. Science fiction calls this the gray goo scenario, but the math suggests it's not just fantasy. Astronomer Frank Tipler once argued that if von Neumann probes were possible, they'd already be everywhere unless something prevents civilizations from creating them. The silence of our galaxy might be a warning sign. Either self-replicating probes are impossible, or every civilization that builds them eventually falls victim to their own creations. Yet the potential rewards could outweigh the risks. These probes wouldn't just map the cosmos, they'd build infrastructure. Imagine arriving at Mars to find a ready-made base constructed by autonomous machines, or reaching Alpha Centauri to discover a swarm of probes has already assembled a telescope array scanning for habitable worlds. They could serve as beacons, relaying data back to Earth through a network spanning light years, or even pave the way for human expansion by prepping outposts on distant worlds. Some theorists suggest they might be the key to contacting alien civilizations. If von Neumann probes are universal, finding one in our solar system could be like discovering a message in a bottle from the stars. The ethics are just as complex as the engineering. Who controls a self-replicating swarm once it's launched? A probe programmed by one nation or corporation could claim resources across the galaxy, effectively monopolizing space before others catch up. There's also the question of contamination. What if a probe accidentally carries Earth microbes to pristine alien oceans? International treaties might require strict safeguards like kill switches to halt replication or quarantines for returned samples. But in the vastness of space, enforcement would be nearly impossible. The moment we unleash self-replicating probes, we're playing with fire on a cosmic scale. The race to build them is already quietly underway. DARPA has funded research into autonomous space manufacturing, while private firms experiment with 3D printers that could one day assemble copies of themselves in zero gravity. Labs are testing AI capable of adaptive problem solving, a precursor to the decision-making needed for interstellar replication. Every breakthrough in robotics or material science inches us closer to the day when a von Neumann probe transitions from thought experiment to launchpad reality. Whether they become humanity's greatest tool or our most catastrophic mistake hinges on one question: can we outthink our own ingenuity? The invention of self-replicating space probes wouldn't just change how we explore the universe, it would force us to confront the responsibility that comes with creating life that doesn't need us to survive. The galaxy might be waiting, but the price of admission could be higher than we realize. History has a way of reminding us how fragile our planet really is. Just ask the dinosaurs. 66 million years ago, a city-sized asteroid slammed into Earth, wiping out 75% of all species. Today, we orbit the same cosmic shooting gallery with over 30,000 near-Earth objects already catalogued. Among them, Apophis stands out, a 340-meter-wide rock that caused a global panic when early calculations suggested a 2.7% chance of impact in 2029. Updated observations ruled out a collision, but the close shave was a wake-up call. Apophis will skim past Earth in 2029 at just 31,000 kilometers closer than some satellites. That's not science fiction. It's a ticking clock reminding us that planetary defense isn't optional. The stakes couldn't be higher. An asteroid like Apophis wouldn't just leave a crater. It would unleash energy equivalent to thousands of nuclear bombs. The shockwave, firestorms, and climate-altering dust could collapse civilizations. Yet for the first time in Earth's history, we're not helpless. NASA's DART mission proved we might be able to nudge danger out of the way. In 2022, a refrigerator-sized spacecraft slammed into Dimorphos, a harmless asteroid moonlet, at 14,000 miles per hour. The impact altered its orbit by 32 minutes, a tiny shift for a rock, but a giant leap for deflection tech. DART was humanity's first intentional act of cosmic self-defense, and it worked better than anyone predicted. But deflection is just one tool in the toolbox. Early warning systems like the Vera Rubin Observatory, set to scan the skies nightly starting in 2025, could give us decades of notice. With enough lead time, even gentle methods like gravity tractors parking a spacecraft near an asteroid to subtly pull it off course with gravity might suffice. For shorter deadlines, nuclear explosive devices remain controversial but effective. Detonating one near an asteroid's surface could vaporize material, creating a thrust that pushes the rock away. The key is flexibility. No single solution fits all scenarios, which is why agencies worldwide are gaming out responses, from the UN Space Mission Planning Advisory Group to ESA's HERA mission, which will study DART aftermath up close. Yet technical hurdles are only half the battle. Planetary defense suffers from a paradox. The more successful we are, the less urgent it feels. Funding dries up when the public forgets the risk, leaving critical projects like next-gen telescopes or deflection prototypes starved of resources. And then there's the geopolitical minefield. Who decides when to act? If China wants to nudge an asteroid while the US prefers a gravity tractor, who gets the final say? The Outer Space Treaty bans weapons of mass destruction in orbit, but ambiguity around nuclear deflection could spark tensions. Even with flawless tech, coordination might be our biggest weakness. The irony is profound. After billions of years of cosmic bombardment, we're the first generation that can look up, not with fear, but with a plan. Every asteroid spotted, every deflection tested, buys us more time in a universe where luck eventually runs out. The dinosaurs didn't have a space program. We do. Whether we use it wisely will determine if our civilization becomes a footnote in Earth's history or a species that learned to steer its own fate among the stars. What if our universe is just one page in an infinite cosmic library? The idea of a multiverse, multiple universes existing alongside our own, has long been dismissed as speculative fiction. But cutting-edge physics is now flirting with the possibility that parallel realities might not be fantasy after all. Take the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. When scientists mapped its subtle temperature variations, they stumbled on something unsettling. A mysterious cold spot spanning billions of light years where the radiation is anomalously faint. One explanation: this could be a bruise left by a collision with another universe billions of years ago, a ghostly imprint of a reality brushing against ours like soap bubbles touching in some higher dimensional foam. The evidence doesn't stop there. Quantum mechanics, the rulebook for subatomic particles, gets bizarre when you scratch beneath the surface. In the famous double-slit experiment, particles behave as if they pass through two paths simultaneously until measured when they choose one. The leading interpretation: every possible outcome happens but in separate, branching universes. This many worlds theory suggests that when you flip a coin, two versions of reality emerge, one where it lands heads, another for tails. These aren't just thought experiments. Labs have run quantum tests showing particles influencing each other instantaneously across distances, as if entangled through hidden dimensions. The math behind string theory takes it further, predicting 10 to the 500 possible universes with different physical laws, a landscape where some might have stronger gravity, reversed time, or even life built on entirely unfamiliar chemistry. Now imagine the shockwaves if we confirmed even one of these theories. Physics textbooks would need rewriting overnight. The constants we thought were fundamental, the speed of light, the strength of gravity, might just be local bylaws in our cosmic neighborhood. Philosophers would grapple with dizzying questions. Are there infinite versions of you making different choices? Does reality split every time a quantum event occurs? Religions might reinterpret creation myths to accommodate a multiplicity of worlds. Even practical fields like computing would transform. Quantum computers already harness parallel states, but full multiverse access could make them unimaginably powerful. Yet the skeptics push back hard. These theories, they argue, often rely on untestable assumptions. That cold spot could just be statistical noise. Quantum oddities might have simpler explanations. But the hunt for proof is accelerating. New telescopes are scanning the cosmic microwave background for more collision scars. Particle colliders are probing extra dimensions. Some physicists even propose that advanced civilizations could leave messages in the fabric of space-time, artificial patterns detectable across universes. Whether the multiverse remains conjecture or becomes fact, the pursuit itself reshapes how we see existence. We're either alone in a single, finely tuned universe or one thread in an infinite tapestry of realities. Either answer is equally profound, equally terrifying. The day we confirm we're not alone in the multiverse might not involve little green men, but something far stranger. The realization that every possible version of reality is out there somewhere playing out in cosmic parallel. And that changes everything. The final frontier may not remain peaceful for long. As nations and corporations stake claims to orbital real estate and lunar resources, the stage is set for a new kind of conflict, one fought not on land or sea, but in the silent void of space. Picture this: a covert cyberattack disables a rival nation's GPS satellites, crippling global shipping and military logistics. Or a missile test shatters a communications satellite, spraying thousands of debris fragments that threaten every spacecraft in low Earth orbit. These aren't hypotheticals, they're scenarios already playing out in war games, from Pentagon briefing rooms to Beijing's strategic think tanks. The line between exploration and escalation is thinning, and the tools of space warfare are evolving faster than the laws to control them. Anti-satellite weapons, once the stuff of spy novels, are now terrifyingly real. In 2019, India's Mission Shakti demonstrated this by blowing up one of its own defunct satellites, joining an elite club including the US, Russia, and China. The immediate effect: a cloud of debris threatening the International Space Station. But the message was clear: dominance in orbit is no longer optional for superpowers. Today's arsenals include more than just missiles. Think killer satellites that sidle up to enemy spacecraft and disable them with robotic arms or microwaves. Some prototypes even harness ground-based lasers to blind optical satellites or fry their electronics. The U.S. Space Force's mysterious X-37B spaceplane, capable of spending years in orbit, hints at platforms that could deploy or repair weapons faster than treaties can keep up. Yet the flashpoints aren't just about weapons. Control over critical orbital zones could spark tomorrow's conflicts. Geostationary orbit, where satellites match Earth's rotation, is prime real estate for communications and surveillance. Only about 1,800 slots exist, and they're filling fast. Then there's the Moon's south pole with its ice deposits. China's lunar landers and NASA Artemis plans are on a collision course, not just scientifically but politically. When multiple nations establish bases near the same scarce resources, tensions won't stay confined to diplomatic memos. The Outer Space Treaty bans nuclear weapons in orbit but says nothing about conventional arms or territorial claims. Legal gray areas this vast are an invitation to brinkmanship. The economic stakes amplify the danger. Modern life depends on satellites for everything from weather forecasts to ATMs globally. The space economy tops $400 billion annually. A single skirmish that takes out key satellites could collapse financial markets, disrupt food supply chains, and blind military reconnaissance overnight. Unlike terrestrial wars, space conflicts could have no clear frontline, with hackers, private companies, and even AI systems becoming players in a chaotic orbital chess match. The irony is brutal. The same technologies enabling asteroid mining and Mars colonies could also turn near-Earth space into a battlefield littered with debris, rendering vital orbits unusable for generations. Deterrent strategies are scrambling to adapt. The U.S. and allies are experimenting with satellite constellations, swarms of small, replaceable satellites that are harder to disable than single high-value targets. Russia and China, meanwhile, invest in electronic warfare and hypersonic missiles that can strike ground stations controlling space assets. Everyone's hedging their bets because the alternative, a free-for-all with no rules, could trap humanity in a modern-day tragedy of the commons where short-term victories poison long-term access to space. The Cold War's mantra of mutually assured destruction kept nuclear weapons in check, but orbital warfare lacks clear red lines. A misinterpreted maneuver or hacked satellite could spark escalation before anyone grasps the consequences. This isn't just about who controls the high ground. It's about whether humanity can avoid repeating its oldest mistakes in a new arena with infinitely higher stakes. The decisions made in the next decade, whether to weaponize orbit or preserve it as a shared commons, will echo through centuries of exploration. One path leads to stars littered with the wreckage of our conflicts. The other, perhaps a future where space unites us in ways Earth never could. But the clock is ticking, and the first shots in a space war might not come as explosions, just a sudden silence where a satellite used to be. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their event horizons, white holes are their theoretical opposites, cosmic fire hydrants blasting out energy and matter with unstoppable force. Picture a region of spacetime where nothing can enter, only escape, vomiting light, gas, and perhaps even entire galaxies into existence. The math of general relativity allows for such objects, but no one's ever seen one. That could change tomorrow if a telescope catches a sudden, inexplicable eruption of energy with no visible source, like a celestial geyser spewing particles at near light speed. The implications would rewrite physics. While black holes trap even light, white holes would defy entropy by generating order from chaos. Some theories suggest they could be the other end of black holes' wormholes connecting distant points in spacetime. Imagine falling into a black hole in one galaxy and being spat out of a white hole in another, effectively teleporting across the cosmos. More radically, white holes might be evidence of time-reversed universes. If our cosmos's Big Bang looks suspiciously like a white hole's explosive output, could our entire universe be the aftermath of some higher dimensional white hole event? The math hints at yes, but the proof remains elusive. Detecting one would require catching its brief, violent outburst. Unlike black holes, which devour matter over eons, white holes would be transient, flashing into existence, expelling their contents, then vanishing. Astronomers might mistake one for a supernova until they notice its light curve doesn't match any known stellar explosion. Or perhaps it would emit particles in patterns impossible for any natural process, like a cosmic fingerprint screaming artificial. The Vera Rubin Observatory, with its nightly scans of the entire sky, could be the instrument that finally spots such an anomaly, yet the philosophical fallout might overshadow the scientific. If white holes exist, they could challenge our understanding of causality, the unbreakable rule that cause precedes effect. Matter emerging from a white hole would have no discernible origin, like a river flowing uphill. Does that mean time could loop back on itself in certain regions of spacetime? Theologians might debate whether white holes are natural phenomena or divine creation acts, while physicists grapple with equations that now resemble ancient myths of eternal cycles. The hunt is already on. Teams scour archival data for unexplained energy spikes, while theorists model how a white hole's gravity would lens background starlight. Some even propose that dark matter, the invisible stuff binding galaxies together, could be the faint remnants of primordial white holes decaying slowly since the dawn of time. Whether these cosmic mavericks are real or just beautiful mathematical ghosts, their pursuit is reshaping how we see the fabric of reality. The day we confirm a white hole won't just add a new object to astronomy's catalogue, it'll tear a hole in our understanding of existence itself. Black holes aren't just cosmic destroyers, they might be the ultimate power plants of the future. Imagine a civilization so advanced it doesn't mine planets for energy, but instead harnesses the unimaginable forces of spacetime itself. This isn't pure fantasy, it's the Penrose process, a real theoretical method to extract energy from a black hole's rotation. Here's how it works. When an object enters the ergosphere, the region just outside a spinning black hole's event horizon, it can split into two pieces. One piece falls in, but if timed perfectly, the other gets slingshot out with more energy than it entered with. The black hole loses a tiny fraction of its rotational energy in the process, and voila, you've just stolen power from the universe's most efficient thief. But why stop there? Quantum mechanics offers an even wilder possibility. Space isn't empty, it's a seething quantum foam where particle-antiparticle pairs constantly pop into existence and annihilate. Near a black hole's event horizon, one particle can fall in while the other escapes, appearing to an outside observer as radiation. This is Hawking radiation, and it suggests black holes slowly evaporate over eons. Now picture a Dyson sphere not around a star, but around a black hole capturing that energy. A stellar mass black hole emits just a trickle of Hawking radiation, but a smaller, artificial one could glow hot enough to power entire civilizations. The catch: we'd need to create and stabilize a microscopic black hole, a feat far beyond today's tech. Yet the math says it's possible. The engineering challenges are as staggering as the rewards. Building a structure capable of withstanding a black hole's tidal forces would require materials stronger than anything known, perhaps woven from cosmic strings or stabilized by force fields we can't yet imagine. Then there's the logistics of feeding matter into the black hole at precise angles to maximize energy extraction without losing your equipment or your engineers to the abyss. Yet the payoff could be exponential. A single optimized Penrose process could yield efficiencies surpassing nuclear fusion, while Hawking radiation offers clean energy with zero waste. For a species facing dwindling planetary resources, mastering black hole energy might be the key to surviving and thriving among the stars. Ethical dilemmas lurk in the shadows. Would artificially creating black holes risk gravitational disasters if one escaped containment? Could harvesting primordial black holes disrupt the fabric of spacetime itself? And who gets to control such power? Corporations, governments, or a coalition of interstellar societies? The very act of tapping into black holes would mark humanity's transition from planet-bound creatures to masters of cosmic forces. It's the sort of technology that doesn't just change how we live, it changes what we are. The groundwork is already being laid. Labs simulate black hole physics using particle colliders and plasma vortices, while theorists refine models of quantum energy extraction. Visionaries like Freeman Dyson speculated about black hole engines decades ago, and today's researchers are crunching the numbers to see how close we can get. Whether it takes centuries or millennia, one thing's certain: the moment we plug into a black hole's power will be the moment we graduate from playing with fire to wielding the fabric of reality itself. Floating effortlessly in zero gravity might look fun in movies, but our bodies were never designed for it. Without the steady pull of Earth's gravity, astronauts face muscle atrophy, bone density loss, and even vision changes after just 6 months in space. If humanity dreams of thriving beyond Earth, whether on Mars voyages or orbital cities, we'll need to reinvent gravity itself. The good news: we already have a working blueprint: centrifugal force. Picture a massive rotating space station, its outer ring spinning fast enough to pin occupants to the walls with force mimicking Earth's gravity. This isn't just science fiction. NASA has been studying designs like the Stanford Torus since the 1970s, and private ventures like Orbital Assembly are now developing commercial stations with spinning habitats. The physics is simple: spin a structure fast enough and inertia does the rest, letting future spacefarers walk, work, and even grow plants as if they were back home. But what if we could generate gravity without the spin? Enter speculative technologies that might one day let us manipulate gravity fields directly. One radical idea harnesses superconductors, materials that expel magnetic fields when chilled to extreme temperatures. Some experiments suggest spinning superconductors could produce subtle gravitational effects, though the results remain controversial. Then there's the Alcubierre drive connection. If warping spacetime enables faster-than-light travel, could we tweak that same principle to create localized gravity wells? Theorists speculate that exotic matter with negative mass might curve space in ways that simulate gravitational pull, eliminating the need for spinning habitats altogether. The catch: we've yet to discover or synthesize such materials, making this a distant but tantalizing possibility. The health implications are staggering. Long-term exposure to microgravity wreaks havoc on circulation, with bodily fluids pooling in the head and torso. Artificial gravity could prevent these issues, making multi-year missions to Mars or decades-long space habitation feasible. Farmers could grow crops in soil that stays put instead of floating away, and children born off-world might develop normally without the skeletal deformities seen in zero-G experiments with animals. Rotating stations could even offer adjustable gravity zones lower for medical recovery or high-G training areas for astronauts preparing for planetary landings. Yet the engineering hurdles loom large. A spinning station must balance rotation speed with comfort. Too slow, and gravity fluctuates unnervingly between head and feet. Too fast, and Coriolis forces cause dizziness and nausea. Early designs suggest a 200-meter diameter with 2 RPMs might mimic Earth gravity without disorienting occupants, but building structures that massive in orbit demands breakthroughs in space construction. Companies exploring in space assembly robots and modular designs could crack this puzzle within decades, turning rotating habitats from concepts into cornerstones of off-world living. The societal ripple effects would be profound. Artificial gravity could make space hotels accessible to tourists unwilling to endure months of floating clumsily, while lunar colonies might feature rotating sections to combat the moon's weak gravity. Militaries could train soldiers in variable G environments, and athletes might push human performance limits in customized gravity fields. The technology wouldn't just protect our bodies, it would redefine how we design every aspect of life beyond Earth. Whether through spinning stations or futuristic gravity generators, cracking this challenge is the silent linchpin of becoming a spacefaring species. Without it, we're forever visitors in space, our biology chaining us to Earth. With it, the cosmos becomes not just a destination but a home. The race to master artificial gravity isn't just about comfort, it's about ensuring humanity can put down roots among the stars and flourish. And that's a future worth building toward, one rotating module at a time. One day, astronomers might point their telescopes at a star and notice something impossible: it's gone. Not exploded, not dimmed, but missing, its light replaced by an eerie infrared glow. The culprit, a Dyson Sphere, a megastructure built by an advanced civilization to harvest every drop of a star's energy. Imagine a swarm of solar panels or a solid shell encasing the sun, capturing its output to power computations, industries, or realities we can't fathom. The concept, dreamed up by physicist Freeman Dyson in 1960, was once pure speculation. But today, as we scan the cosmos for unusual heat signatures, we're actively hunting for these cosmic fingerprints of alien engineering. The search hinges on thermodynamics. Stars emit visible light, but a Dyson sphere would absorb that energy and irradiate it as waste heat. Infrared wavelengths detectable across interstellar distances. In 2015, astronomers stumbled on a star called Tabby's star, whose light dimmed erratically by up to 22%. Natural explanations, dust clouds or swarms of comets, never quite fit. Could its flickers be the shadows of unfinished Dyson components under construction? Then there's the bizarre case of 2 stars identified by the Gaia spacecraft, whose infrared excesses defy known astrophysical models. These anomalies don't confirm alien megastructures, but they're the closest thing we've got to a cosmic, under-construction sign. Finding one would rewrite our place in the universe. A fully enclosed star suggests a civilization millions, maybe billions of years ahead of us, capable of manipulating matter on a planetary scale. The energy demands alone hint at unimaginable ambitions. Are they powering planet-sized computers simulating entire realities? Building interstellar arcs for migration, or perhaps they've transcended physical forms, existing as pure information in a star-encompassing digital hive. The scale dwarfs human history, like ants discovering a skyscraper and realizing something far greater walks the Earth. Yet the implications terrify as much as they awe. A species that can dismantle planets for building materials is unlikely to see us as peers. Some theorists warn that Dyson spheres could be beacons of predation, advanced civilizations expanding inexorably, consuming stars like a swarm of locusts. Others argue they're more likely dormant relics, their builders long since evolved into something beyond our comprehension. Either way, the moment we confirm one isn't just about discovery. It's about realizing we're sharing the cosmos with entities whose motives and morals might be as alien as their technology. The hunt is accelerating. Projects like Glimpsing Heat from Alien Technologies analyze telescope data for infrared outliers, while SETI tunes its antennas to stars with excess heat, listening for encoded signals in the waste energy. Even failures teach us. Each ruled-out Dyson candidate refines our understanding of astrophysical phenomena, sharpening the tools we'll need to spot the real deal. One day, the data might reveal a star wrapped in geometric perfection, its light too orderly for nature alone. And on that day, humanity will face a choice. Do we hide, reach out, or start building our own sphere before someone else claims our sun? The first baby born beyond Earth won't just make history, they'll redefine what it means to be human. Picture a delivery room orbiting high above Earth, where doctors in magnetic boots monitor zero-gravity fetal development, and the newborn's first cries echo through a sterile module instead of a planetary hospital. The biological hurdles alone are staggering. On Earth, gravity guides fetal positioning. Without it, childbirth could become a high-risk procedure requiring artificial centrifugal pods to simulate gravitational pull during labor. Bone and muscle development in utero might falter without constant resistance, leading to weaker skeletons. Even something as simple as a baby's first breath becomes complicated when fluids don't drain naturally in microgravity, risking pulmonary complications unheard of on Earth. But the challenges don't stop at biology. Legal frameworks crumble when you ask, what nationality is a child born in orbit? The Outer Space Treaty declares celestial bodies free from national claims, but says nothing about humans conceived off-world. If the birth occurs on a U.S.-registered spacecraft, does the baby automatically get American citizenship? What if the parents are from different countries, or the vessel is owned by a corporation rather than a state? Early spacefaring nations might rush to establish orbital birthright laws, sparking jurisdictional battles that could strand these children in bureaucratic limbo. And what happens when the first off-world toddler reaches voting age? Will they have representation in Earth's governments, or will they demand independence, forming the first space-bound political bloc? The societal ripple effects could be profound. A generation raised without ever feeling wind or sunlight might develop radically different perceptions of home. Their vestibular systems, adapted to microgravity, could find Earth's pull unbearable, rendering visits to their ancestral planet a nauseating ordeal. Culturally, they might identify more with their orbital community than any terrestrial nation, sparking new art, languages, and even religions framed by the endless vistas of space. Over centuries, genetic divergence could occur, subtle at first, like increased height from unconstrained growth, but potentially leading to speciation if reproductive isolation continues. These changes wouldn't just create a new branch of humanity, they'd forge an entirely new chapter in evolution. Ethical firestorms await the pioneers who attempt this. Is it fair to subject an infant to untested developmental risks for the sake of colonization? Religious groups might debate whether souls can be born outside God's chosen planet, while bioethicists clash over the right to impose a lifetime of physical adaptation on an unborn child. Yet the momentum is building. Private companies like Space Life Origin have already floated plans for orbital conception and birth, while NASA quietly studies mammalian reproduction in microgravity. Every mouse pup born healthy on the International Space Station inches us closer to the day when a human takes their first breath in the void. This milestone won't just change one life, it will force humanity to confront questions we've never had to ask. Are we Earth-bound creatures venturing outward, or are we on the brink of becoming something new? The first space-born child won't just carry their parents' DNA, they'll carry the weight of a species stepping off its cradle world, ready or not. And once that threshold is crossed, there's no going back. The moment humanity makes contact with an intelligent species not of this Earth, every assumption about our place in the universe shatters. This isn't just about decoding alien radio signals or spotting a distant spacecraft, it's about confronting beings whose very existence challenges the foundations of human culture, language, and belief. Picture scientists staring at a live feed from a probe on Europa, watching bioluminescent tendrils weave intricate structures in the subsurface ocean, reacting to the camera with unmistakable curiosity. Or imagine radio astronomers isolating a signal so packed with mathematical complexity that it can't be natural static, but a deliberate attempt to communicate. The immediate question wouldn't be what we've found, but who and what they want from us. Language itself becomes the first battleground of understanding. Human communication evolved around shared experiences, sunlight, predators, the need for shelter. But what if these beings perceive reality through echolocation, magnetic fields, or dimensions we can't access? Their language might not even be auditory. It could be patterns of color shifts, quantum entanglement states, or chemical exchanges. Early attempts at translation would resemble the Rosetta Stone project on steroids, with AI scrambling to find common reference points. The breakthroughs would redefine linguistics. Imagine discovering that their concept of time is non-linear, or that they convey entire histories through fractal melodies. The very act of deciphering their thoughts could expand human cognition, forcing our brains to adapt to modes of thinking we never knew existed. Then comes the theological earthquake. For millennia, religions have centered on humanity's special relationship with the divine. What happens when we're no longer the only souls in the cosmos? Some faiths might reinterpret scripture metaphorically. Perhaps the angels described in ancient texts were visitors all along. Others could fracture, with fundamentalists rejecting the aliens as demonic deceptions while progressives embrace them as proof of a grander creation. New hybrid belief systems might emerge, blending extraterrestrial science with spiritual awe. The Vatican's observatory has already convened panels on astrotheology, while Buddhist scholars ponder whether enlightenment applies to silicon-based lifeforms. The existential shockwaves would ripple through every house of worship, seminary, and home, forcing a reckoning with the divine that no holy book anticipated. Politically, contact could unite or divide like nothing before. Initial reactions might mirror historical first encounters on Earth: fear, fascination, or exploitation. Governments would scramble to establish protocols. Do we broadcast our location in reply, or heed Stephen Hawking's warning that advanced civilizations could be predatory? The United Nations Office for Outer Space Affairs has draft guidelines for alien contact, but could a planet still fractured by borders and ideologies present a unified front? Corporations might see dollar signs in alien tech, while military strategists panic over vulnerabilities. Meanwhile, grassroots movements would erupt, xenophobic factions demanding isolation, interstellar embracers forming cults around the newcomer's wisdom, or scientists pleading for open collaboration. The very notion of us versus them would stretch to cosmic scales, testing whether humanity can overcome its tribal instincts when faced with the ultimate other. And what if they're nothing like us? Hollywood aliens often mirror humanoid shapes with slightly altered features, but reality could be far stranger. Beings of pure energy, hive minds spanning planets, or creatures living in quantum superposition would force us to expand our definition of intelligence. Their morality might seem incomprehensible. Perhaps they see no ethical issue with repurposing asteroids filled with life as raw materials, or they view war as a beautiful cosmic dance. Their mere existence could expose human biases we never knew we had, like the assumption that all intelligent life values individuality, progress, or even survival. The cultural vertigo would be profound, akin to medieval sailors learning the Earth isn't flat, except this time the ground keeps shifting underfoot. Yet in this chaos lies an opportunity unlike any in history. Contact could catalyze a global identity transcending nationality, race, or creed. We'd all become Earthlings overnight. Shared astonishment might dissolve ancient grudges, as arguing over borders feels trivial when faced with a galactic perspective. Our art, philosophy, and science would explode with new inspiration, fed by alien mathematics, aesthetics, or technologies. Children would grow up fluent in interspecies diplomacy, while universities scramble to establish xenobiology departments. The shock could even propel us toward planetary stewardship, realizing how fragile and precious our lone blue world truly is when seen through alien eyes. The irony is piercing. After centuries of wondering if we're alone, the answer might reveal how interconnected we've always been, not just as a species, but as part of a tapestry of consciousness spanning the stars. Whether the encounter is peaceful or perilous, one thing's certain: the day we meet them, we'll finally meet ourselves, and that mirror, however unsettling, could be the making of us. Time bends where gravity and speed stretch it thin, a quirk of Einstein's relativity that could turn interstellar travelers into time travelers. Picture identical twins saying goodbye at a rocket launch. One boards a ship accelerating to 90% light speed for a 10-year round trip to Proxima Centauri, while the other stays on Earth. When the astronaut returns, only a decade has passed for them, but back home, their sibling is an elderly stranger, having aged 25 years or more. This is the twin paradox, not a thought experiment, but an inevitability etched into the fabric of space-time. The faster you move through space, the slower you move through time, and the effects become dramatic as you approach light speed. A voyage lasting years for the crew could span centuries on Earth, transforming homecoming into an archaeological dig through the ruins of familiar eras. The mechanics behind this are both simple and mind-bending. Special relativity reveals that time isn't universal, it's personal, flowing at different rates depending on your velocity. Atomic clocks on GPS satellites hurtling at 14,000 kilometers per hour tick marginally faster than ground-based ones, requiring constant adjustments to stay accurate. Now amplify that speed. At 99.9% light speed, one ship year equals 22 Earth years. Push further and the ratios grow exponential. A 5-year trip at 99.999% light speed could return you to a planet where 15,000 years have evaporated. Civilizations might rise and fall between your departure and return, leaving your mission logs as cryptic relics to whatever society remains. This isn't just theory. Particles in Earth's atmosphere, accelerated to near light speeds by cosmic rays, decay slower than their stationary counterparts, a phenomenon confirmed in labs with subatomic particles. Apply that to human travelers and the implications are staggering. Generational ships become unnecessary if time dilation compresses subjective travel time. A crew could reach Andromeda in a lifetime. Their lifetime, though 2.5 million years, would pass in their wake, but the cost is brutal isolation. Every outbound journey becomes a one-way trip into humanity's future, severing ties to everyone and everything left behind. Letters home would arrive millennia late, and even radio waves would stretch into indecipherable whispers across the gulfs of time. The emotional toll would redefine exploration. Imagine raising children on a ship where Earth is a mythic homeland from history books, or returning to find your great-great-grandchildren debating whether your era was legend. Time dilation could birth entire cultures of void-born humans, psychologically untethered from planetary timekeeping, measuring lives in light years rather than years. Religions might venerate near-light-speed travelers as prophets who have touched the divine, having witnessed epochs flash by like days. Or perhaps they'd be feared as ghosts of a dead past, stumbling into futures that have no place for them. Here's the cruel twist: relativity offers no loophole for the traveler. While Earth's clocks race ahead, the astronaut's experience feels utterly normal. Meals, sleep, birthdays all unfold at their usual rhythm. Only the universe beyond the ship's walls betrays the ruse, with stars ahead blue-shifted to oblivion and those behind fading into infrared graves. Navigation itself becomes a nightmare as centuries of stellar motion distort the constellation's mid-journey. A crew calibrated for Alpha Centauri's position at departure might find its drifted light years off course by arrival, swallowed by the galaxy's relentless churn. Yet buried in this temporal chaos lies an eerie opportunity. Time dilation could be the ultimate time capsule, preserving crews to awaken in distant futures, whether as pioneers or specimens. A ship launched today at near light speed might return in 100,000 years, carrying intact records of 21st century culture to a post-human world. Or it could become a tomb, its crew perishing in transit only to be recovered by descendants who have long forgotten their names. The same physics enabling interstellar travel also ensures its loneliness, severing travelers from the very civilizations they hope to serve. Governments and corporations would face impossible choices. Do they greenlight missions knowing crews can never truly come home? Will astronauts sign contracts agreeing to return to unrecognizable worlds, or will they demand one-way glory like ancient explorers crossing uncharted seas? Legal systems might grapple with temporal inheritance, where a traveler's assets sit frozen for centuries until their biological return, heirs long turn to dust. And what if a ship arrives to find Earth barren, its people vanished or evolved beyond recognition? Time dilation doesn't just bend clocks, it twists the soul of exploration into something bittersweet and profoundly alien. The stars have always beckoned, but relativity whispers a warning. Some journeys change the traveler more than the destination. Every tick of a ship's clock is a trade, a piece of the universe's time borrowed against the future. And the bill comes due the moment the engines cut off, leaving explorers stranded in a new age, forever outsiders to the flow of human history they once called home. The sun may seem like a steady, unchanging presence in our sky until it isn't. In 1859, a solar storm so powerful erupted from its surface that telegraph systems across Europe and North America spontaneously caught fire, operators receiving shocks through their equipment as auroras blazed as far south as Cuba. This was the Carrington event, named after the astronomer who witnessed its origin. A solar flare so intense, its associated coronal mass ejection bombarded Earth with charged particles at speeds exceeding 4 million miles per hour. Back then, the damage was limited to sparks and disruptions, but today, a storm of that magnitude wouldn't just fry telegraph wires. It could plunge the modern world into a technological dark age. Solar flares are explosions of magnetic energy on the sun's surface, while coronal mass ejections are billion-ton clouds of plasma hurled into space. When these eruptions align with Earth, the results are anything but benign. The Carrington event was a warning shot. A similar storm today would induce ground currents strong enough to overload power grids, frying transformers that take years to manufacture and replace. Satellites in orbit, zapped by radiation, their electronics scrambled into uselessness. GPS signals would distort or vanish, crippling everything from air travel to precision agriculture. Even undersea internet cables, the backbone of global communication, could fail as geomagnetic currents surge through their conductive sheaths. Experts estimate the economic toll could reach trillions, not in decades but in days. The terrifying part: we're overdue. Solar activity follows an 11-year cycle with periods of intense eruptions known as solar maximum. But superstorms like Carrington are rare, occurring roughly once every century and a half. The last near miss came in 2012 when a tsunami of comparable strength missed Earth by just 9 days. Had it struck, the world would still be picking up the pieces. And while agencies like NOAA monitor space weather, our early warning systems grant us mere hours, not enough to shield critical infrastructure. Transformers, for instance, aren't built with surge protection. Replacing a single one can take 18 months. Now imagine hundreds failing simultaneously across continents. The aftermath would resemble a slow-motion catastrophe. Without power, water pumps stop working, refrigeration fails, spoiling food supplies, hospitals scramble to keep life support systems running on dwindling generators. Financial markets freeze as electronic transactions become impossible. And with satellites disabled, weather forecasting reverts to 19th century methods, leaving coastal communities blind to approaching hurricanes. The cascading failures could last years, unraveling supply chains and societal trust. Unlike a pandemic or earthquake, this disaster wouldn't be localized. It would be global, relentless, and utterly indifferent to human suffering. Yet there's a glimmer of hope. Some nations are fortifying their grids. Finland installed Faraday cages around critical transformers, while the US has begun stockpiling spare parts. Scientists are developing advanced forecasting models, and SpaceX's Starlink satellites now feature radiation-hardened electronics. The ultimate solution might lie in space-based deflectors, giant magnetic shields positioned between Earth and the Sun, a concept once relegated to sci-fi but now under serious study. But progress is slow, underfunded, and fragmented. Until the next Carrington-scale storm hits, we're essentially gambling with civilization's future, hoping the sun's fury won't align with our vulnerability. Here's the sobering truth: the sun doesn't care about our technology. It's a roiling ball of plasma, following laws of physics we're only beginning to understand. The Carrington event wasn't an anomaly, it was a preview. Whether the next megastorm strikes next year or next century, one thing's certain: when it does, humanity will face a test unlike any in modern history. The question isn't if we'll see another solar superstorm, it's whether we'll be ready when it arrives. Wormholes aren't just the stuff of sci-fi dreams, they're a legitimate prediction of Einstein's equations. The math suggests these cosmic tunnels, known as Einstein-Rosen bridges, could act as shortcuts through the fabric of spacetime, connecting distant points in the universe like a folded piece of paper pierced by a pencil. Imagine stepping into a portal near Earth and emerging near Alpha Centauri in seconds rather than millennia. Theoretically, a stable wormhole could render light speed limits irrelevant, turning interstellar travel into a subway ride across the cosmos. But here's the catch: the same equations that allow for wormholes also demand conditions so extreme they border on fantasy. Creating or finding a traversable wormhole would require exotic matter with negative energy, a substance that defies gravity instead of obeying it. Think of it as cosmic duct tape propping open the wormhole's throat against the relentless crush of spacetime trying to snap it shut. While quantum mechanics hints at fleeting instances of negative energy, like the Casimir effect between ultra-close plates, scaling this up to stabilize a wormhole would mean harnessing energies beyond anything our technology can muster. Even then, the slightest imbalance could collapse the tunnel mid-transit, spaghettifying anything inside into an atomic smear across dimensions. Then there's the navigation problem. Unlike black holes, which naturally form from dying stars, wormholes don't come with roadmaps. If one exists, it might be microscopic, buried in the quantum foam of spacetime, or floating light years away in some uncharted void. Early attempts to detect them involve hunting for gravitational lensing anomalies, regions where light bends in ways no black hole or dark matter could explain. Some theorists suggest advanced civilizations might engineer artificial wormholes, leaving behind telltale radiation patterns or spacetime ripples detectable by next-gen telescopes. Others speculate that primordial wormholes forged in the Big Bang's chaos could still lurk in deep space, relics of a universe more interconnected than we ever imagined. Yet, even if we found one, the paradoxes pile up. Time dilation near a wormhole's mouth could create scenarios where exiting the tunnel sends you back to before you entered, violating causality. Picture shaking hands with your past self at the exit, or worse, accidentally preventing your own birth by altering a critical event in history. The universe tends to recoil from such violations, potentially triggering quantum corrections that erase the wormhole, or the traveler, from existence. Physicists debate whether these paradoxes are fatal flaws or just puzzles waiting for a smarter species to solve. The implications of a working wormhole stretch beyond travel. It would redefine cosmology, suggesting our universe is punctured with hidden passageways, some leading to other galaxies, others to entirely different universes with alternate physical laws. Philosophers would grapple with whether each wormhole mouth is a distinct location or just two facets of the same twisted spacetime geometry, and militaries. They'd treat them as strategic choke points more valuable than any oil field, sparking conflicts over who controls the ultimate high ground. For now, wormholes remain tantalizingly out of reach, suspended between mathematical elegance and engineering nightmares. But the hunt is on. Experiments with quantum entanglement and spacetime foam probe the edges of possibility, while telescopes scour the skies for anomalies that don't fit the cosmic mold. The day we confirm a wormhole's existence won't just rewrite physics. It'll force us to confront a universe far stranger and far richer than we ever dared to dream. Picture a constellation of mirrors and panels floating 36,000 kilometers above Earth, silently soaking up sunlight unfiltered by atmosphere or night. These aren't just ordinary satellites, they're the backbone of the first space-based solar power grid, each array spanning kilometers and converting photons into microwaves beamed precisely to receiving stations on the ground. Unlike terrestrial solar farms limited by weather and daylight, these orbital power plants operate 24/7, capturing up to 40 times more energy per square meter than their Earth-bound counterparts. The technology isn't science fiction. Japan's JAXA successfully transmitted power via microwaves in 2015, and Caltech's Space Solar Power project recently launched a prototype capable of wirelessly relaying solar energy from orbit. What sounds like a utopian energy solution could soon rewrite the rules of global power literally. The engineering challenges are as vast as the potential. Launching gigawatt-scale arrays demands lightweight, modular designs. Think origami-like panels that unfold in space, or swarms of smaller satellites synchronized like a hive mind. The real magic lies in the microwave beams. These aren't the sci-fi death rays of popular imagination, but low-intensity waves tuned to frequencies harmless to life. Their energy absorbed by rectinas, specialized ground antennas converting microwaves back into electricity. Safety protocols would ensure beams automatically shut off if they stray off target, and locating receivers in remote deserts or offshore platforms minimizes risks. The hurdles, yes, they're towering, like avoiding signal degradation from atmospheric interference or scaling up transmission efficiency beyond current 50% benchmarks. But the payoff could dwarf the Apollo program's legacy. Geopolitically, this is a game changer. Nations tethered to fossil fuel imports, whether oil, gas, or coal, would gain energy independence overnight. Imagine the Middle East's petrostates pivoting from oil derricks to rectenna farms, or Europe ending its reliance on volatile gas pipelines. Even developing nations could leapfrog traditional grid infrastructure, receiving clean power beamed directly to rural communities without laying thousands of miles of vulnerable transmission lines. The ripple effects would destabilize old alliances and forge new ones. Oil cartels might scramble to diversify their economies, while countries with prime orbital slots over the equator, where sunlight is most consistent, could become the new energy superpowers. The phrase energy war could vanish from the lexicon, replaced by orbital access treaties and solar beam leasing agreements. The environmental upside is just as transformative. With carbon-free energy flowing from space, Earth's land could be liberated from industrial-scale solar and wind farms, rewilding millions of acres. No more raising forests for biofuel crops or damming rivers for hydropower. Even the energy-intensive process of removing carbon dioxide from the atmosphere becomes viable when powered by an essentially infinite clean source. But there's a catch. Launching thousands of solar satellites could strain the rocket industry's carbon footprint unless we pivot to green propulsion like reusable rockets or lunar-mined hydrogen. The irony of burning fossil fuels to end fossil fuels isn't lost on engineers, but once the first arrays are operational, they'd pay back their launch emissions within months. Economically, the shift would be seismic. Utility companies might transition from selling energy to managing rectenna networks, while aerospace firms race to build and maintain orbital assets. New industries would bloom like space-based maintenance drones repairing solar arrays, or AI systems optimizing beam distribution across global grids. Consumers could see energy costs plummet as supply outpaces demand, akin to how the internet slashed communication expenses. But monopolies loom as a danger. Will this technology be a public good or controlled by corporate giants charging premium rates for priority beam access? Regulatory frameworks don't yet exist to ensure equitable distribution, and the specter of orbital debris damaging trillion-dollar arrays adds a layer of fragility to what should be a resilient system. Skeptics often cite the massive upfront costs, but history offers a counterpoint. The transcontinental railroad and interstate highway system once seemed impossibly expensive, yet they underpinned centuries of economic growth. Space Solar's price tag, estimated at tens of billions to start, pales next to the trillions spent annually on fossil fuel subsidies and climate disaster recovery. And the tech is advancing faster than critics predict. Private ventures like Solstar aim to deploy small-scale demonstrators by 2030, while China's Omega project plans a functioning megawatt-scale station by 2035. Every breakthrough in photovoltaics, robotics, or wireless transmission inches this vision closer to reality. What makes this more than just an energy revolution is the domino effect it triggers. Abundant clean power could make water desalination affordable for drought-stricken regions, enable carbon-neutral synthetic fuels for aviation, and even power the first magnetic levitation space launchers, reducing the cost of reaching orbit itself. The same technology might one day supply lunar bases or Mars colonies, with arrays orbiting those worlds instead of Earth. But the most profound shift could be psychological. For the first time, humanity would be harnessing the cosmos not just for exploration but for survival. The day Earth's electricity grids sync to orbital sunlight isn't just about turning off fossil fuels. It's about turning on a future where energy scarcity and the conflicts it fuels become relics of a dimmer age. What if we're not the first intelligent species to call this solar system home? The Silurian hypothesis dares to ask a startling question. Could evidence of a prior advanced civilization be buried right beneath our feet, or more accurately, hidden in the rocks of Mars, the dunes of Titan, or the rubble of the asteroid belt? Named after an old Doctor Who episode featuring ancient reptilian beings, this idea isn't just wild speculation. Paleontologists and astronomers have seriously debated whether industrial civilizations might have risen and fallen on Earth millions of years before humans, or even on other worlds, leaving behind traces we've yet to recognize. The unsettling truth: fossil records are shockingly incomplete. After just a few million years, tectonic activity and erosion can erase nearly all physical evidence of a civilization. If a species built cities 100 million years ago, we might never find their ruins, just as future archaeologists might miss ours if humanity vanished today. This isn't about little green men, it's about subtle forensic clues. On Earth, scientists hunt for technofossils, unusual chemical signatures or material layers that defy natural explanations. Think of synthetic molecules like chlorofluorocarbons lingering in ancient ice cores, or spikes in rare metals from large-scale mining operations frozen in sedimentary rock. But Earth's geology is a blender, constantly recycling its crust. The real jackpot might lie off-world. Asteroids, untouched by erosion or plate tectonics, could preserve relics for billions of years. Imagine a prospecting drone cracking open a metallic asteroid only to find unnaturally patterned alloys or machinery fragments older than Earth itself. Even stranger, the Moon's surface, bombarded by solar radiation but geologically dead, might hold artifacts undisturbed since the solar system's youth. Apollo mission archives contain curious anomalies like the Moon's spectacles, two glassy spheres found in lunar soil with no clear volcanic origin. Could they be industrial byproducts from a forgotten epoch? The implications would dwarf any archaeological discovery in human history. Finding even a single corroded gear in the asteroid belt would prove intelligence isn't unique to Earth, and worse, that advanced societies might be fragile, prone to self-destruction or cosmic disasters. Some theorists suggest this could explain the Fermi paradox. If civilizations rise, expand, and inevitably collapse, the galaxy might be littered with their undetected ruins. Others take it further. What if remnants of their technology still function? The mysterious interstellar object Oumuamua, with its bizarre acceleration and shape, sparked debates about whether it was a derelict solar sail or probe. While natural explanations exist, the possibility lingers. We might be sifting through the ashes of a civilization that once thrived between Mars and Jupiter before vanishing into cosmic oblivion. Asteroid miners could become the accidental archaeologists of tomorrow. Corporations scouring space rocks for platinum might stumble upon artifacts that rewrite history, like a cube of purified titanium lodged in a carbonaceous chondrite, or a crystalline data storage device waiting to be deciphered. The ethical dilemmas would be monumental. Do we treat these sites with reverence or dismantle them for raw materials? Would governments classify such finds to prevent panic, or would the discovery unite humanity in humbled awe? Legal frameworks don't exist for extraterrestrial antiquities, leaving a vacuum where scientific curiosity could clash with corporate greed. The search itself forces us to reconsider what evidence even means. Alien technology might not look technological to us. It could resemble self-replicating nanoscale structures mistaken for odd minerals, or dormant bioengineered organisms hiding in Martian permafrost. Some Silurian hypothesis proponents argue we should scan the solar system for isotopic anomalies, like traces of plutonium-244, a radioactive element non-existent in nature but a byproduct of advanced fission. Others suggest looking for stellar engines, megastructures aliens might have built to harness a star's energy, leaving heat signatures detectable by telescopes. Whether the hypothesis holds water or not, its value lies in the perspective shift. We're forced to confront the fragility of intelligence. that even starfaring civilizations might leave only whispers in the cosmic wind. The next time a rover drills into Martian clay or a miner's laser slices open an asteroid, they might uncover more than resources. They could reveal that humanity's story is just one paragraph in a much, much older book, one whose previous authors vanished without a trace. Imagine sending a message to a Mars colony and receiving an instant reply, not after the agonizing delay of up to 22 minutes that light-speed signals impose, but immediately, as if you were texting someone across town. This isn't a violation of physics. It's the revolutionary promise of quantum communication networks, where the bizarre properties of entangled particles could rewrite the rules of interplanetary communication. At the heart of this technology lies quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, their properties, like spin or polarization, are linked, no matter how far apart they separate. Change one particle's state, and its partner reacts instantaneously, even if it's light years away. This eerie connection defies classical physics, but could become the backbone of an unhackable, real-time messaging system spanning the solar system. The breakthrough hinges on quantum repeaters, devices that extend entanglement across vast distances. On Earth, fiber optic cables and satellite links already transmit quantum keys for ultra-secure encryption, but space offers a pristine environment for entanglement to flourish. Without atmospheric interference or signal degradation, pairs of entangled photons could be distributed between Earth, Mars, and beyond using specialized satellites. Picture a network of quantum relays in orbit around each planet, constantly refreshing entangled pairs to ensure uninterrupted connections. A diplomat on Mars could negotiate with Earth's leaders with zero lag, or scientists on Europa's ice-covered oceans could stream data to mission control without the bottleneck of traditional radio waves. The speed of diplomacy, trade, and even personal communication would leap from the pace of the Pony Express to the immediacy of a video call. Security is where quantum networks shine brightest. Unlike conventional signals that can be intercepted or spoofed, quantum messages are fundamentally tamper-proof. Any attempt to eavesdrop on an entangled photon disrupts its state, alerting both sender and receiver to the breach. This could prevent interstellar espionage or sabotage of critical infrastructure, from asteroid mining ops to off-world power grids. Military strategists already envision quantum-secured command systems for space fleets, where orders can't be decrypted or falsified by adversaries. But the implications stretch beyond defense. Banks might use quantum channels to settle transactions between planetary branches, while media companies could stream ultra-high-definition footage from Jupiter's moons without piracy concerns. Yet the technical hurdles are as daunting as the potential. Maintaining entanglement over interplanetary distances requires near-perfect isolation from cosmic noise. Solar flares, micrometeorites, or even the faint tug of a planet's gravity could decohere the delicate quantum states. Solutions might involve cryogenically cooled satellites or error-correcting algorithms that salvage corrupted entanglement. Then there's the no-cloning rule of quantum mechanics. Unlike traditional data, quantum information can't be copied for redundancy. Lose a photon to deep space, and that piece of the message is gone forever. Engineers are racing to develop quantum memory units that can store fragile states long enough for retransmission, a challenge akin to catching smoke with your hands. The geopolitical stakes are equally high. The first nation or corporation to deploy a functional quantum network would wield unprecedented influence, controlling the scaffolding of off-world communication. Imagine a scenario where Earth's quantum satellites are incompatible with Mars-based systems, forcing colonies to rely on a single provider's infrastructure, a 22nd century version of a telecom monopoly with dominion over the speed and security of interstellar discourse. International treaties don't yet address quantum bandwidth rights, leaving a legal vacuum that could spark conflicts over who owns the right to entangle photons across sovereign space zones. Already, the race is heating up. China's Misha satellite demonstrated entanglement distribution over 1,200 kilometers in 2017, while the EU's Quantum Internet Alliance aims to link European cities via quantum channels by 2030. Private ventures like Quantum Space want to position repeaters in lunar orbit, and NASA Jet Propulsion Lab is testing quantum receivers for deep space missions. Every successful experiment pushes the boundary of what's possible, inching us toward a future where a back and forth with a Martian outpost feels as seamless as chatting with a neighbor. But the true revolution might be cultural. Instant communication could collapse the psychological distance between worlds, making Mars settlers feel less like pioneers on an isolated frontier and more like participants in a connected interplanetary society. Families split across planets could share daily moments in real time, and global solar collaborations in science or art would flourish without latency's frustrating barriers. The moment humanity achieves quantum networking among the stars won't just mark a leap in technology. It'll redefine what it means to stay close in an era when home isn't just one planet but many. And that's a future worth entangling ourselves in. For centuries, Proxima Centauri has been little more than a faint red dot in our telescopes, the closest star to our sun, yet forever out of reach. That barrier is about to shatter. Projects like Breakthrough Starshot aren't just planning to send a probe to another star. They're redefining what's possible, using a fleet of gram-scale nanocraft propelled by ground-based lasers to accelerate to 20% the speed of light. Picture a postage stamp-sized probe thinner than a sheet of paper riding a beam of photons like a cosmic surfboard. Within just 20 years, it could be skimming past Proxima Centauri's potentially habitable planet, Proxima b, snapping images and collecting data that would take conventional probes tens of thousands of years to obtain. This isn't just a mission, it's a message in a bottle hurled into the cosmic ocean, proving that humanity's curiosity can outpace the vastness of space itself. The challenges are as thrilling as the ambition. These nanocrafts, or starships, must survive interstellar dust impacts that could shred them like shrapnel, endure the crushing acceleration of 60,000 G-forces, and somehow transmit day to 4.2 light-years back to Earth with a laser weaker than a smartphone's flashlight. Every component pushes the edge of physics sails made of atom-thin metamaterials that won't melt under laser bombardment. Onboard cameras no larger than a grain of salt, yet capable of resolving continental features on an alien world. Even the laser array itself, a kilometer-scale installation firing gigawatt pulses, represents a feat of engineering rivaling the pyramids, except these monuments won't point at the pharaohs but at the stars. Yet the payoff could ignite a new era of exploration. The first close-up image of Proxima b's terrain, whether frozen deserts, vast oceans, or something entirely alien, wouldn't just fill textbooks, it would electrify public imagination. Imagine a child seeing jagged crimson mountains under a dim red sun, realizing for the first time that other worlds aren't just dots in the sky, but places with landscapes and skies of their own. Data on atmospheric composition could reveal biosignatures, gases like oxygen or methane that hint at life's presence. Even a barren vista would carry profound weight, proving that Earth-like worlds can exist right next door, waiting for the next wave of explorers. The ripple effects would extend beyond science. A successful interstellar mission could unite nations under a shared technological triumph, much like the Apollo program did, but this time the flag planted won't be cloth on lunar soil, but photons piercing the void between stars. Private investors, inspired by the mission's audacity, might pour funding into radical propulsion research, from antimatter drives to nuclear pulse engines. Universities could see a surge in astrophysics enrollments as a generation raised on interstellar probes dreams of following them into the unknown. And if Proxima b shows even the faintest hint of habitability, the debate shifts from "can we go?" to "when do we leave?" But here's the twist: the data might not arrive in our lifetimes. Even at light speed, transmissions from Proxima Centauri take over 4 years to reach Earth. A probe launched today might not send its findings until the mid-21st century, leaving its creators to wait, wonder, and perhaps never see the fruits of their labor. Yet that's the paradox of interstellar exploration. It demands patience even as it defies limits. The architects of Starshot understand this. They're not building for accolades, but for the long arc of human progress, knowing that the images and readings from Proxima b won't just inform the next mission, but echo across generations, whispering, "This is only the beginning." The moment that first data packet arrives, whether it's a hazy photo or a spectroscopic analysis, will mark a pivot in history. Not because we'll have all the answers, but because we'll finally know the right questions to ask. Proxima Centauri won't just be a destination then. It'll be the first stop on a roadmap written in starlight, beckoning us outward. And somewhere in the static of that transmission, we might hear something even more profound: the future calling back. Betelgeuse, the fiery red shoulder of the Orion constellation, has been ticking like a cosmic time bomb for millennia, and the countdown could end any day. This colossal star, 900 times the size of our Sun, is teetering on the edge of collapse. When it finally explodes as a supernova, the spectacle will be unlike anything humanity has witnessed in recorded history. For weeks, a second sun will blaze in our daytime sky, casting eerie shadows at noon and outshining the full moon at night. Ancient cultures might have interpreted such an event as a god's wrath or a celestial omen. Tomorrow's astronomers will reach for their spectrometers instead of myths, measuring the flood of neutrinos and gamma rays heralding the death throes of a stellar giant. The science behind this impending fireworks show is as violent as it is beautiful. Betelgeuse has already exhausted the hydrogen and helium in its core, fusing heavier elements like silicon and oxygen in a desperate battle against gravity. When the final collapse comes, the star's core will rebound in a shockwave so powerful, it shreds the outer layers at speeds exceeding 30,000 kilometers per second. The blast will release more energy in seconds than our Sun emits over its entire 10 billion-year lifespan. Earth, safely distant at 640 light-years, won't face physical danger, but the electromagnetic aftermath will ripple through our technology in unpredictable ways. Satellites orbiting Earth would bear the brunt of the assault. The initial neutrino burst, harmless to life but detectable by underground labs like Super Kamiokande, would be followed by a torrent of high-energy particles and X-rays. Our planet's atmosphere shields those on the ground, but unshielded electronics in space could be fried by the radiation surge. GPS signals might flicker as satellites reset their fried circuits, while communication networks relying on geostationary relays experience delays or outages. Hubble and James Webb would likely shut their delicate optics to prevent damage, temporarily blinding our deepest views of the cosmos during the most spectacular astronomical event in centuries. Yet the cultural impact could eclipse even the technological disruptions. Imagine social media flooded with hashtags like #2suns as influencers and amateur astronomers alike post side-by-side comparisons of Betelgeuse and the Sun. Artists would reinterpret Van Gogh's Starry Night with a second luminous orb, while poets muse on the fragility of existence under a sky that can suddenly rewrite itself. The event would transcend borders, religions, and languages, offering a rare moment of collective awe in a fractured world. For the first time in history, a stellar death wouldn't be recorded in scrolls or cave paintings, but in terabytes of smartphone footage and petabytes of telescope data, a democratization of cosmic witness. Astronomers are already preparing for this once in a civilization observation. Every major observatory from Chile to Hawaii has contingency plans to pivot their instruments toward Orion the moment neutrino detectors sound the alarm. Citizen scientists will play a role too, with apps like NASA, a comet hunter adapted to log Betelgeuse's brightening. The data gathered could solve long-standing mysteries about how massive stars seed the universe with elements like gold and uranium, the very atoms in our jewelry and nuclear reactors. But lurking beneath the excitement is a humbling truth. Betelgeuse might have already exploded. Its light takes 6 centuries to reach us, meaning the star could have met its fiery end when Chaucer wrote the Canterbury Tales. We're watching the past unfold in real time, a reminder that the night sky is a mosaic of cosmic ghosts and delayed telegrams. Whether the detonation comes tomorrow or in 100 years, one thing's certain: when it does, humanity will look up together, united under the glow of a dying star's farewell. And in that shared moment of wonder, we'll confront a paradox. The same event that threatens our satellites might also remind us why we reached for the stars in the first place. What if everything we perceive, every galaxy, every atom, even our own thoughts, is just a flickering projection on the edge of some unfathomable cosmic canvas? This isn't the plot of a sci-fi movie. It's the holographic principle, a radical theory gaining traction as astronomers uncover bizarre anomalies in the fabric of reality itself. The idea hinges on a mind-bending proposition. The 3-dimensional universe we experience might be encoded on a 2-dimensional surface at its boundary, like a movie playing on the walls of a vast, unseen theater. Evidence for this comes from unexpected corners of cosmology, particularly the study of black holes. When matter falls into a black hole, theoretical physics suggests its information isn't destroyed but smeared across the event horizon, the point of no return, like ink staining a spherical sponge. If a black hole's contents can be encoded on its surface, why not the entire universe? Clues hiding in plain sight seem to support this. The cosmic microwave background, the afterglow of the Big Bang, holds temperature fluctuations that shouldn't exist if space were purely 3-dimensional. Some scientists argue these patterns resemble interference fringes, the kind you'd see in a hologram where overlapping light waves create the illusion of depth. Even more startling, certain quantum entanglement experiments reveal particles influencing each other instantaneously across vast distances, as if they're not separate entities but pixels on a shared screen refreshing faster than light. These phenomena don't just challenge Einstein's relativity, they hint at a deeper, more interconnected reality where locality and distance might be illusions. The implications would rewrite existence from the ground up. Time and space could emerge from something more fundamental, like how a 3D image emerges from flat data on a credit card hologram. Gravity might not be a force but a side effect of information density gradients. Think of it as cosmic pixelation becoming more noticeable near massive objects. Even consciousness itself could take on new meaning. If reality is a projection, is our perception of free will just part of the code? Philosophers and physicists alike are grappling with these questions, some suggesting that the universe isn't just described by mathematics, it is mathematics running on a substrate we can't yet perceive. Skeptics, of course, push back. The holographic principle remains untested in key areas, and alternative explanations exist for the anomalies, yet experiments are underway to probe deeper. Fermilab's holometer sought to detect Planck-scale fuzziness in spacetime, evidence of its pixelated nature, while future quantum gravity experiments might look for signatures of lower-dimensional encoding in high-energy particle collisions. Even our telescopes play a role. If the universe's large-scale structure shows unexpected statistical patterns, like a repeating resolution limit, it could hint at underlying digital architecture. Whether the holographic principle holds or not, its mere possibility forces us to confront the unnerving idea that reality might be far stranger than it appears. The day we confirm it wouldn't just revolutionize physics, it would collapse the boundary between science and metaphysics, leaving us to wonder, if we're living in a cosmic projection, who or what is holding the projector? The snap of a space elevator cable wouldn't just echo through the atmosphere, it would send shockwaves across every nation on Earth. Imagine this: after decades of construction and trillions invested, the first operational space elevator suffers a structural failure at the midway point. The carbon nanotube tether, thinner than a ribbon but stronger than steel, frays under an unforeseen stress, perhaps a micrometeoroid impact, a hidden manufacturing flaw, or resonant vibrations from a passing storm. In seconds, 36,000 kilometers of cable whip backward, lashing across the equator like a scalpel slicing through orbit. The climber pod, loaded with passengers and precious cargo, plummets into the ocean or careens into space, depending on where the break occurs. But the real devastation comes from the tether itself. As the severed segment falls, it wraps around the planet at hypersonic speed, slicing through satellites, space stations, and anything else in its path before crashing into the anchor station, or worse, a populated area. The aftermath isn't just an engineering failure, it's a geopolitical earthquake. The immediate toll would be measured in lives and infrastructure, but the long-term consequences could paralyze space development for generations. Nations that bankroll the project face financial ruin, their economies crippled by lawsuits and the collapse of orbital industries reliant on cheap elevator access. Insurance markets, already wary of space megaprojects, might refuse coverage for future elevators, stranding blueprints in bureaucratic limbo. Meanwhile, the environmental fallout, tons of high-tech debris scattered across land and sea, could trigger international disputes over liability and cleanup. Imagine Ecuador, whose territory hosts the anchor station, demanding reparations from the consortium that built the elevator, while Malaysia accuses neighboring countries of negligently allowing debris to cross airspace. The incident becomes a cautionary tale about the fragility of global cooperation when tragedy strikes beyond Earth's borders. Lessons would emerge from the wreckage, reshaping engineering standards forever. Future designs might incorporate segmented tethers with emergency detachment points, allowing controlled brakes that minimize collateral damage. Redundant safety systems like electromagnetic brakes or parachute arrays for falling climbers could become mandatory. The accident might also spur innovations in real-time monitoring. Think fleets of inspection drones patrolling the tether for microfractures, or AI algorithms predicting stress failures before they happen. But the hardest shifts would be psychological. Public trust in megastructures would shatter overnight, forcing proponents to confront uncomfortable questions. Should humanity keep reaching for the stars if the price of failure is so catastrophic? Can we ethically risk lives on projects that blur the line between ambition and hubris? Yet history suggests we'll press forward. The Titanic's sinking didn't end ocean travel, it revolutionized maritime safety. The Hindenburg disaster didn't halt airships, it refined them. A space elevator failure, however devastating, might ultimately teach us how to build not just taller but wiser. The next attempt won't just aim for the sky, it'll carry the weight of every mistake etched into its design, turning tragedy into the foundation for something more resilient. And in that stubborn persistence, we'll prove once again that humanity's greatest innovations often rise from the ashes of its most spectacular failures. Humanity's first steps beyond the Milky Way won't be taken by astronauts, they'll be taken by the descendants of astronauts, born light years from Earth aboard ships designed to outlast civilizations. Generation ships, colossal arcs carrying thousands of passengers across millennia, represent one possible path to Andromeda, our nearest galactic neighbor 2.5 million light-years away. Picture a self-contained ecosystem the size of a city, with artificial gravity generated by rotation, hydroponic farms feeding generations of travelers, and libraries storing the collective knowledge of Earth alongside new cultures born in transit. These vessels wouldn't just transport people, they'd become floating time capsules, preserving human identity while evolving it into something unrecognizable to those left behind. The ethical weight is staggering. Every child born aboard would inherit a mission they never chose, bound to die in the void between galaxies without ever setting foot on a planet. Yet the alternative, never venturing beyond our cosmic neighborhood, could mean stagnation, leaving humanity's fate tied to a single galaxy's lifespan. Warp drives offer a tantalizing alternative, bending spacetime to cheat the light-speed barrier. If Alcubierre's theoretical designs ever transition from paper to reality, crossing intergalactic distances could shrink from millions of years to mere decades. But even at 1,000 times light speed, Andromeda remains a 2,000-year journey, still spanning generations unless we crack suspended animation or AI-guided probes capable of reconstructing human settlers upon arrival. The energy demands defy comprehension. A warp bubble large enough for a crewed ship might require the mass energy of Jupiter, forcing us to harness black holes or antimatter factories just to fuel the leap. And then there's the existential risk. What if the technology works, but the universe's topology prevents safe passage? Wormholes could collapse mid-transit, or exotic matter could destabilize, stranding travelers in the incomprehensible gulf between galactic filaments. The moment we breach the Milky Way's halo marks a turning point in cosmic history. Unlike starships venturing to nearby systems, intergalactic travelers would gaze back at a home galaxy shrinking into insignificance, its spiral arms blending into the background stars. Earth itself would fade from memory, its continents and conflicts reduced to myth. New social structures might emerge aboard ships or colonies, perhaps hive-mind collectives linked by neural networks or fragmented tribes warring over dwindling resources in the abyss. Art and religion would grapple with scales beyond human intuition, venerating the void itself as a deity or interpreting Andromeda's looming disk as a promised land. Yet the greatest challenge isn't distance or technology, it's purpose. Why endure such hardship when no urgent threat compels us? The answer might lie in entropy itself. Stars die, galaxies cool, and black holes evaporate over trillion-year timescales. Spreading beyond the Milky Way isn't just exploration, it's cosmic insurance, ensuring that supernova, gamma-ray bursts, or the eventual heat death of our home galaxy don't spell the end of consciousness. Each intergalactic colony would become a backup drive for the human experiment, diversifying our chances against universal calamity. Whether by generation ships, warp bubbles, or technologies we can't yet imagine, the leap to Andromeda signals more than a physical journey. It's the ultimate declaration that humanity refuses to be bound by any horizon, no matter how vast. The ships we launch today, or the blueprints we draft, carry the dreams of a species that looked at the impossible and whispered, "Not for long." From the discovery of habitable exoplanets to the explosive potential of solar superstorms, these 30 space events aren't just distant possibilities, they're the hinges on which the future of humanity could swing. Imagine standing at the edge of a cosmic domino effect, where one breakthrough, whether it's the birth of the first off-world child, the invention of a warp drive, or the detection of an alien signal, sets off a chain reaction that reshapes civilization. Some events, like asteroid deflection or Mars colonization, are already within our grasp, their timelines measured in decades rather than centuries. Others, like intergalactic travel or harnessing black hole energy, exist at the fringes of known physics, daring us to push beyond the limits of what we think is possible. Yet each one, no matter how near or far, holds the power to redefine not just where we live, but who we are as a species. Think about the ripple effects. Contact with extraterrestrial life wouldn't just answer the age-old question of whether we're alone. It could spark theological upheavals, unite nations under a shared cosmic identity, or thrust us into a galactic community with rules we don't yet understand. The construction of a Dyson Sphere around our sun wouldn't merely solve Earth's energy crisis, it would mark our transition from a planetary civilization to a stellar one, capable of harnessing the power of stars. Even quieter milestones like the confirmation of a white hole or the discovery of ancient alien ruins in our solar system would quietly rewrite textbooks, forcing us to confront the unnerving idea that the universe is stranger, richer, and more interconnected than we ever dreamed. But here's the most thrilling part: we're alive for this. For the first time in history, humanity stands on the threshold of events that could echo across millennia, and we get to witness or even shape their unfolding. That's why your voice matters. Which of these 30 events excites you the most? Is it the prospect of cracking faster than light travel, or the spine-chilling possibility of a rogue planet barreling into our solar system? Maybe it's the quiet revolution of quantum communication networks, or the dystopian specter of a space war fought over orbital real estate. Drop your thoughts in the comments. We're all part of this conversation, and the future is too big to ponder alone. If these cosmic possibilities lit up your imagination, don't let the journey end here. Hit that subscribe button to dive deeper into the mysteries of the universe, from the physics-defying to the downright mind-bending. Because the next world-changing event might not be centuries away. It could be in tomorrow's headlines, and you won't want to miss it. The stars aren't just points of light anymore. They're destinations, puzzles, and maybe even partners in the greatest story humanity will ever tell. Let's explore them